Okay, so starting over again, I'm explaining for students in office hours how an AVL tree works at several different levels of abstraction at once. So the history of it is that I have a hash table that have been into the late 50s, and right around the same time, late 50s, early 60s, that's when binary search trees start. So binary search trees are meant to be a compromise. With a hash table, we have a lot of memory, but we have this hash function that allows us to be able to look up locations very fast and big all at one time. With a linked list, we have our data heap, and then based on that, we have some sort of this pointer. We have a head, which initially points to a location. Let's call this 10, and singly linked list head 20, 30, and the benefit is, let's say this memory comes available, we can do 40 here. So that's a singly linked list, and everything that we have there allows us to be able to find empty locations in the memory and be able to put things there. Benefit of the hash table, fast, speed. Benefit of the linked list, memory. So we have time complexity and space complexity. So now the question becomes, how do we find a good mix of these? Now we're thinking ourselves early, mid 60s, space race, thoughts on high performance and low memory. We got to figure out how to do both. And that's where trees come into play. So we learned in class about basic ideas of trees and how they work. So there came up a problem. What happened is, I'm going to draw up over here, I'm going to draw a data heap and some in a register. And then over here on the algorithmic level, I'm going to write up the actual how the tree's working. So if I put in 10, 20, and 30, what we're seeing is it takes a lot longer to do 30 than 20, right? And the further I go, if I put them in the exact order, 10, 20, 30, 40, 50, and so on, it becomes a glorified linked list, except now all of the left pointers are all null. So we get none of the memory benefits and none of the search time for us as the list gets longer. So this is where the inventors of the AVL tree come around. I don't remember now, it was 1962. 1962, right after binary search trees have been implemented, they're saying, all right, well, we have this 10, 20, 30 scenario. Ideally, what we'd like to have happen is this becomes 20, 10, and 30, because now we have found balance for the tree. And I just realized, no, that's right. No, I thought I was broadcasting it with the mirrors, so all the letters were backwards. But here's what's happening at the physical level. So we have this pointer, which we use when we encapsulate in the class, and it's pointing to what we're going to call the root. And that's a EST node pointer. And when I insert 10, it's going to give me 10, and then I'm going to have two pointers for left and right. So root's going to point to 10, and if I insert 20, 20 is now going to be here. Right is going to be pointing to 20, but you see how 20 is not point 10, the left one's not pointing to anything. 30 has the same situation, and we will stick with that for now, so that way I'm going to insert 40 and 50. So here's what's happening. I have to figure out how to get from here to here, but how to do it physically. So what's going to happen is we're going to say, all right, I'm going to come up with some temporary pointers and perform a swap. So I'm going to create pointers for, I eventually need to point to 20, and I need to point to 10, and I need to keep track of the root. I can't lose anything. I need to, when we are done, we need to be able to find anything in the tree. So here's what's going to happen. I am going to create a pointer that points to the root, a pointer that points to 10, and a pointer that points to 20. See, these are all temporary pointers. When we go out of the scope of the function, these are all going to go away. So what I want to do is I'm going to say, well, I eventually want 20 to be my new root. So I am going to have root here now point to 20. So far we've updated it. Now when I start the tree, the initial thing that I find is going to be 20. The next thing that I need to do is I need to figure out how to rearrange it so that way I maintain the ordering to perform this rotation. So at the algorithmic level, we see that 20's left child could potentially hold 10. And that's what we want, because I can move this down here. So 20's left child, which right now is null, is now going to point to 10. So 20's left child is now going to be set equal to this particular pointer. So now 10's right child is going to point to where 20's left child was pointing, which is null. So now this goes away. And this is going to work because 10 is going to be a leaf, and therefore both of its children should be null. So now we have that updated. 20's right child is now 30. Both of these are null, just like it represents. And then what's going to happen is we're going to go out of the insertion scope. And now we can compare the physical level, or the architectural level, with the algorithmic level. We see that we have the root is 20. And then if I want to go left, I go to 10. If I want to go right, I go to 30. So now we have our first set of information on the AVL. So now I'm going to insert two more. I'm going to insert 40 and 50. So let me move this up. We've got 20, 10, 30, and I'm going to insert 40 and 50. If I'm inserting, I'm going to switch colors here so we see how this works physically. If I'm inserting 40, I go to there, right? Pretty simple. Here's what's actually going on physically. I go here, I go to the root, I go to 20. 40 is greater than 20, so I go right. 40 is greater than 30, so I go right. This is null. So therefore, what I'm going to do is I'm going to create a temporary node. So when I create a temporary node pointer, it's allocating a register and pointing here. I create two children, and then I say, well, 30's right child needs to point to 40. And so when it does that, now 40 goes here, and now this will go out of scope. And now we have the tree so far. Now I'm going to do the same thing with 50. 50 would go here. 40's right child points at 50. So now it looks like this. Does that make sense so far? So now what we're going to do is we are going to say, well, we get here, and on the right, I have 2, and on the left, I don't have any. So I have a localized imbalance here. In order to solve this problem, and I want to perform this rotation, I'm going to draw out what our destination will be, and then I'm going to work through it step by step. So the destination should be 20, 40, 30, 50, and 10. Make sense? So what do we need to know from get here to here? I eventually need 20. I eventually need this pointer to point here. You see that? I eventually need this one to point to 30. So now I need to come up with the same process where I have these temporary pointers, where one of them is going to point at 20. One of them is going to point at 30. And one of them is going to point at 40. So now we're going to perform this update. 20's right child is initially pointing at 30. I now know that I want it to point to 40. So we still maintain this because we still have these 3 temporary pointers. So now 40's left child, which is currently not pointing at anything, needs to point to 30. And 30's right child is going to point to what 40 was pointing to before, which is null. So now we have this particular setup. And so now, here's what we have on the right. Once these go out of scope, once the function's done, now what I have is root goes to 20, 20 on the left goes to 10, 20 on the right goes to 40, 40 on the left goes to 30, 40 on the right goes to 50. So now what we're doing is we're translating a physical strip of memory into logically binary tree. So now let's see how much I can actually confuse this machine a little bit, right? So the question becomes, well, what happens if I insert 35? Right? So you have 30 here, 35. And I start moving up. What's going to happen is I got 2 over here and 1 over there, so we don't violate the balance. But now what's going to happen is I'm going to go to 3 and 1. So now we have this rule that's been violated. So how do we make this work? So initially what's happened is 35 is going to be here, right? And now 30's right child is pointing at 35. So now the question is, well, how do I perform that balance while simultaneously ensuring that I don't screw everything up and keep it in order? So let's discuss possibilities. First, what we're going to say is, well, here I have 3 and here I have 1. And here I have 2 and I have 1. And ideally, what I'd like to have is 2 and 2. So it makes all the sense in the world to go over to the larger side and try to get this moved up. So I want to start here with 40. But how do I ensure that I don't get this to be too high, right? So what's going to happen is, if I have 50 over here, that's now just 1. So we see that there's a potential problem there. And if I move this to, if I select 30, I make this as 20 and 10, and I put 35 over here, well, look what we have. We actually have 3 and 1 again. So that didn't work out. So this is where this idea of zigzag comes into play. What if instead of 40 at the top, I put 30 at the top? Let's see what happens there. So if I move 30 to the top, and we want to maintain the ordering, what can I do? Well, I could have 20 here and 10. Now I've got 2. Now, let's look at the rest of these. We got 35, 40, and 50. So if I move this up, what I can then say is, well, if I do 35, 40, and 50, we have 2 and 3, which doesn't violate anything at the top, but we do have 2 and 0 here, which is a violation. So here's what I propose we do. What if we did this instead? What if I did 40, 35, and 50? Now, what I have is I've met all the balancing from over here. I have 2 and 2 on both sides, 1 and 1, 1 and 0, 0 and 0. So the entire tree now has balance. That make sense? Awesome. So now the question is, well, how do we get from here to here? So initially what happened is I have 1, 2, 3, and I have a root, right? So now I need to figure out how to make everything work. So at this point, what I'm going to do, I'm going to redraw down here 20, 10, 40, 30, 35, and 50. And we're going to say great-grandparent, grandparent, parent, child, right? So now what I want to do is I'm going to use this particular graph, this particular tree to get to this tree. Because the tree that I just circled is the one that's physically represented here. So now let's translate. I know that I want the root. So I'm going to have the root here, and I'm going to have another one point to 20, and I'm going to have another one point to 40, and I have another one point to 30. Okay. So now the question is, how do I get from first one to second one? Well, the first one, we see that the one that's pointing at root should now be pointing at the child, right? So the one that was pointing at root, instead of pointing at 20, it should now be pointing at 30. So now I'm going to update this root pointer to move to point to 30. So far, so good. The next question is, well, how do I rearrange this? So child right needs to be pointing here. 40 should point to 35. So 40's left is currently pointing at 30. See that? We don't need that anymore because now we're not pointing at it. So what I would do is the first thing I would have here, this is how I would put it up, is I'd say, well, now 40's left is going to point to 35. And now I say 30's right instead of pointing to 35, since that's now no longer necessary, is going to point to 40, which is what's pointing here. So that's how we've updated that so far. So now 40's right points to 50, 40's left points to 35, 30's right points to 40, but we still have one thing we need to do. 30's left isn't pointing at anything. And this makes sense because initially in the tree, 30's left was null. 20's right is also pointing to 40. 20 was initially the grandparent. That's this one, right? So now what we need to do is we need to make 30's left equal to the grandparent, which is what's going to happen there. And then we can update 20. 20's right, which was pointing there, is now going to point to null, which is what we want because we see that it's null there. So now what we have, if I remove this and I were to reverse engineer it from the physical level up to the algorithmic level of abstraction, here's what this tree physically represents. This tree physically represents, we have a pointer that's pointing to the root. So we have a root. Root now points to 30. 30's left will point to 20. 20's left points to 10. 10's children are both null. 20's right child is null. Now we go, by 30, we go right. We see that 30's right child points to 40. 40's left child points to 35. Both of 35's children are null. And then 40's right child points to 50. And both of 50's children are null. So now what we see is we've now constructed the tree properly. So when you are trying to figure out how an AVL tree works and how to study it, and this is the same thing with B trees. Too many students get hung up on memorizing rules. You see how I didn't say, all right, well, this is rule 3, we follow this step. I don't have those rules memorized, but I was able to know what they were based on translating the algorithmic level of abstraction to the physical level. And once everything made sense, like, okay, in order to keep track and not lose track of everything, I need to create these 3 pointers so that they're all pointing everything. And then I did it this way, the rules fell into place. Like I'm quite confident that if you went back over everything, that the rules I came up with and presented in class, I did them in the exact order, because it made sense, because I had to keep track of what pointers went where. So if you can, my recommendation for you is you study AVL trees, dig into how they fit together. How would you start it somewhere, try to get to, so in this case, this is where I started it, and this is where I wanted to get to make it work. What would I actually need in order to make that happen? Does that make sense? Mm-hmm. So if you can do that, and you can make it translate this way, you will be able to handle any problem I throw at you on a test. Let me